And now we're going to go to our second speaker, Randy Beaudry from Michigan State University, and he works a lot on post-harvest fruit quality and storability. So Randy, the screen is all yours.
Thanks a lot. Thank you for the invitation and the opportunity to share a few comments. So a lot of what I'll share today is mostly historical in nature and really more of an interview than any overview, than anything else. But I think you might find it interesting. So let's go through what I have to share. So I was asked to talk about the impact of heat on fruit maturation and storability. I'll focus a little bit on both, but before I get into that, I want to talk a little bit, very briefly, about climate and weather. I think everyone here probably understands that there's quite a bit of difference between climate and weather. And weather is what you face on a year-to-year basis, day-to-day basis, and climate and long-term trends. Absolutely interrelated, because the extremes in weather, as climate change decides that we're going to be in a warmer climate in the future, those weather extremes become greater. So they're linked, and I'll kind of break up my comments, talk a little bit about climate, and then I'll sort of break into some of the more weather-related responses that you might see, let's say, within a single season. What you see on the screen right now is an analysis that myself and some colleagues have done on the temperature, the global temperature for the planet as it changes throughout the months. And so we did this for evaporative cooling purposes, by the way, so that might be kind of interesting for the folks that are interested in that particular area, but I'm just showing you here the dry bulb temperature and how it shifts throughout the season. So you can see there's dramatic shift in this particular case. But looking at that, we started to address the question, well, what the heck is going to happen in the future? So if we take the models, the weather models that currently exist, and then predict the future, what does that look like in terms of both temperature, evaporative cooling potential, and then potentially then lethal temperatures as well, not only for plant materials, but also for humans as well. So one of the things that we decided to do, and I think, is to kind of look at the weather models that are out there and say, well, how accurate are those weather models? And so this was our first step into this particular area. So each one of these histograms that are kind of embedded one within the other here is a summation of tens of millions of data points, just so you know. So this is not something I did. This is something an engineer did in India on this particular project. But the things that I wanted to point out are kind of interesting here. So one of the things that we did was predict what the 10-year average looks like for the past 10 years versus the previous 10 years. Not looking at climate change here, just to look at how accurate those predictions are for a given location on the planet. And you can see in this lower quadrant here that it's 0.30 degrees plus or minus 0.49 degrees. So one decade to the next, very, very similar kinds of data points. Then when we looked at the 10-year average versus a single year, so in a single year, you're going to see more variation. You can see that the spread is a little bit larger. Now we're at about the average. So the average difference in temperature from predicted is 0 basically here, but a 1 degree difference in the prediction from the actual. So then when we looked at our weather models, now keep in mind that these are the weather models that were based on this data plus an additional 10 years worth of data to predict what's going to happen 50 years in the future and 100 years in the future, okay? So the first question we asked was, how well do these weather models predict what actually happened? So we just chose a year, 2012 in this particular case, and this is the month of July, which is important for us. And you can kind of see what happens when you start using weather models to predict the weather that has already happened. You can see that the variation is really quite large. So the accuracy of the weather models for an individual point and an individual place is really, really broad. It's not accurate. It's rather broad. The overall trends are probably quite accurate, but in terms of saying, in this particular case, you're going to have this particular weather, you cannot count on it. It's just too darn variable. So then so as I mentioned, so we were interested in what was going to happen in the future. And so these are some of the weather models here that are important. So the CESM model, you don't really need to know those. The top one is probably considered to be the best of the models that we have. So in 2050, Here's once again our prediction in the middle here with a 1 degree variation. So that's our actual 10-year average versus the actual 2012. So if this is a really accurate prediction, you should see something that looks a little bit like this. You know, we're predicting an average temperature for 2050. And what do we find? A lot of variation. So now our variation is actually increased a bit. So 3 degrees plus or minus 3 degrees plus or minus 3 degrees. But you'll see that 2 of the models predict that the temperature is going to be higher in the future, and then one of them predicts a lower temperature for the planet, which is interesting. Not by much, but by a little bit. Then by 2100, you can see that the variability that's depicted by these predictions continues to increase. So once again, 2, 3, and 3 degrees here difference, but they all predict, all of the weather models that are currently in existence that we had evaluated anyway, but they're all based on the same data sets, predict about about a 3 or 4 degree increase in temperature. So 2.5 degree increase, a 5 degree increase, and a 3 degree increase in temperature over the years to come. So that's just background. So we can't tell what's going to happen in one particular place very well. It doesn't predict its own self very well, but it does show a really strong trend, and all of the climate models seem to agree what's going to come down the pipe. Okay, well, what does that mean? So we're going to transition here a little bit to kind of say the more weather-related things, even though understanding that those we might understand that those trends are in existence. And one of the earliest pieces of information I was able to find was this particular study here by Creasy at Cornell University. And what they did is they took several years worth of data and they looked at the color development. And I believe this is for, I think it was Macintosh apple fruit. And what you see is for any given stretch of days, they could look at the accumulation of anthocyanins in the skin of the fruit. And they developed this really nice temperature relationship. So you'll see that the temperature is lower out here to the right and higher off to the left. So it's a little bit backwards of what we normally think. But as the temperature increases and gets up to 65 degrees Fahrenheit or better, that the color development seems to slow. So this was one from field data, and then they did the same work in controlled environment chambers, and they got basically the same data, that the best color development was down at these lower temperatures, the 55 degrees, the 60 degrees temperature range, and then basically was almost non-existent in some cases when the temperature got over 75 degrees on average for a day. So pretty alarming when you think that our temperatures in the fall might be increasing as dramatically as they are, and then for the variability of a year to year, so the year to year variation, I should say, makes that even more pertinent. So this is a article that was produced recently by Stefano from out west in your neck of the in Washington State. So and they have a few comments that I would like to summarize here. Sorry, they have a number of different publications that they cite, and this is one of the citations here. This was a work that was done in Germany in 2009. And what they noticed was that early maturing cultivars over this period of time that they evaluated, and I think it was 40 years in their particular case, they now ripen 3 to 4 days earlier, while later cultivars ripen 8 to 12 days earlier. So we're looking at these trends that are occurring with these warmer temperatures in the fall. So a warm fall is associated with the early ripening, and it can be pretty dramatic, anywhere from 3 days to 12 days, depending on the apple variety. And this is kind of what their data look like. So if you take a look at this, it's kind of impressive data to be able to go back into their records and pull this kind of data out and then share it. So here's our annual mean temperatures that they were looking at. So you can see these long-term trends for this particular research site. So oh, I'm sorry, this is a separate study. I'm going to confuse myself again and again. I'm sorry, I just rushed into this, I think. This was out of Japan. And in this particular case, yeah, they looked at it over 40 years. And what they found was that taste and textural attributes have changed as a result of the global warming. And these are the characteristics that they looked at. So they looked at titratable acids over time, soluble solids over time for 3 different areas within their country. And what they found was that there are these definite and distinct trends The ones that they show here are significant in terms of statistical relevance. But over the 40 years, you can see that the soluble solids have increased over time somewhat. Now that kind of flies in the face of some predictions that the higher temperatures might lead to or should lead to lower soluble solids as the sugar is burned up. But in this case, I think they're attributing it to the fruit being more mature at harvest, and so more starch conversion has taken place. But you can see the trends that exist over time for these flavor associated characteristics. And fruit firmness going in the opposite direction. So for the different areas, no significant, well, it's a significant trend, but not probably a very meaningful trend here in one particular area, the Aomori area. But you can see the nice declines in firmness over time as the fruit softened from 6 down to 5 kilograms. Excuse me just a second, I got to wipe this out. Stuck with it. Okay, and then the other thing that was kind of unpredictable, or not predicted, I should say, is that water core declined. So the amount of water core that was present in the fruit declined. And once again, this might have been associated with higher rates of respiration at the higher temperatures that they're experiencing over time, but also the harvesting of more mature fruit. So they had less and less water core over the 40 years of this study. So they took this data and then they back calculated for the average temperature for the year and took a look and looked for trends that are specifically temperature related, not just yearly trends, right? But those that could be associated with temperature. And they found that there was an association between the acid concentration, so the tartness or the sharpness of the flavor, versus the average temperature for the season. And then they also found that fruit firmness declined in this particular case where the trend is shown as a function of temperature. So as the temperature got higher, the fruit firmness was lower. So you're seeing kind of in with 40 years worth of data, the distillation into these trends that are telling us what to expect on a warm year versus a cool year. And then, like I say, once again, when they looked at the temperature data, and this is kind of remarkable, actually, is just the amount of water core, the relationship, I should say, between fruit temperature as a function of the seasonal temperature, and then what happens to this water core susceptibility. And the temperatures that they're looking at here are strictly during the latter half of the season, so during what they call the maturation phase. So higher temperatures during the maturation period lead to these differences, as they say, in soluble solids concentrations. And yeah, they're depicting it to this maturation period, high temperatures. So the latter half of the season is what they're really focused on for this piece of work here. So they were concerned about climate as well. And in this particular case, they summarize their comments or their findings and suggest that, yeah, we need to be more concerned about qualities of apple fruit in the market over the long term. And what I take from this is that what we really need to do is make sure that we focus on all the tools that we have, everything we can to maximize quality if it's a warm year versus a cool year. The challenges are higher and the risks are higher. So we need to do everything right and reduce mistakes to an absolute minimum. I wanted to make a couple of comments here about this is some old data that I had collected back when I first started at Michigan State. This is back in 1993. And one of the other comments I wanted to make was that, we think and focus on those latter stages of development when I think about post-harvest, so the ripening phase. And in this case, I'm not going to focus on the data out here. This is red and golden delicious here. But this is Macintosh apple fruit here. So what you see is this decline from early August through September of Macintosh firmness. Now, Macintosh, as far as I know, has never hit retail shelves more than about 15 or 16 pounds pressure. But they're starting out here at 19 pounds pressure. And of course, we're much firmer than that just a few weeks before that. There are remarkable changes in the firmness of the fruit that aren't necessarily associated with the changes in fruit size or cell size happening very early relative to the maturation phase, which in this case is actually somewhere in early to mid-September for us here in Michigan. So a lot of firmness is lost, a lot of texture is lost. And so what this means is that these are developmental changes that are taking place, and we need to be cognizant of those. And so this really fits in with that Japanese study that I just talked about, the idea that the weather during these later periods can really affect the final firmness that we find ourselves facing in the harvest season. So we're coming out with a starch index scale here at Michigan with cooperation with storage control systems. And this is something I just wanted to, I said, lay out. So I'm working on with Emily Lively with it on this, as well as Nikki Rothwell. And it's kind of a nice project, but I wanted to kind of highlight what we know about maturation or maturity. Every cultivar differs from every other cultivar. So if you look at the starch staining pattern and you want to understand where you are relative to the development of that, you have to look at the cultivar itself and understand how these patterns change. And so for this particular reason, we came up with starch stain indices for, I think it's 12 different cultivars that we grow here in Michigan and some that are grown out west as well. So that's just a setup to show this particular data here. And this data is from 3 different years for Michigan Gala apple fruit. And what we're seeing is the changes in the starch index, very similar to the kind of starch index that you saw there a moment ago, changes from 1 up to 9. So you can see that in 1996, 97, the patterns were very similar. 1998 was a very warm year, and you can see that that increase in starch index, the developmental phase was offset by nearly 2.5, 3 weeks. Okay, so season really dramatically impacts some varieties, and Gala especially is one of those varieties that seems to be overly sensitive to temperature. 2010 was even more dramatic. We had the fruit off the tree before the students started in classes here at Michigan State. I did an analysis of a number of different years from 2007 to 2017 for a presentation I gave up in 2017 up in Northwest Michigan. And what you're seeing here, the growing degree day accumulation for all of those years as a function of time. And what I put into crosshairs here is the number of growing degree days for I would consider to be a normal maturation of Gala fruit. So they would be expected to be harvested somewhere in mid-September. So this would be the onset. And what you can see is that from year to year, the growing degree days that we accumulate, at least here in Michigan, can vary from very excessive to very minimal. Okay. So in terms of the overall season, we can see points in time or seasons where we never achieve the necessary heat units in some cases. In other cases, we have an excess of heat units. So once again, pointing out just how important it is to understand where you are relative to the development of the apple or the variety. And in 2017, in particular, I wanted to point this out. So that September 6th date is right about here. So this is when we're beginning to think about harvesting Gala apple fruit. And you can see that in 2017, we had a relatively cool summer. I mean, if you see most of the data points for all of those other years is a little bit higher in terms of growing degree date accumulation. And then we had this spike in temperature where the temperatures went up in the mid and upper 90s for a period of time. Those Gala fruit that were harvested here early before the spike stored extremely well. Those that were harvested after the spike in temperature really suffered. And those high temperatures that we experienced at that time, the lack of color development that pushed back further color development and caused further delays in harvest really caused our crop to suffer in that year. And this is one example from that year. And it's one of those horrible things nobody wants to see, but it's really an object lesson. So this is a bin, one of many bins of Gala fruit that were stored here in Michigan in 2017, when everything that could possibly go wrong kind of went wrong for that particular grower. Late harvest, high field temperatures, slow cooling because the fruit were warm and it was difficult to cool them down and they had difficulties getting the heat out of the room. Delayed MCP, and then I would add to that there was a lack of monitoring by the storage operation. So all of those things put together. So we have 5 conditions that were working together, and this is the result when those kinds of things happen. So we need to be on the ball all the time. So temperature control is really important. I would just stress that once you've got those fruit off, if they're warm, cool them down, get them under control as soon as you possibly can, storability increases 2 to 3-fold for each 10 degrees Celsius drop in temperature. So that means that this holds for those time periods, even when you're trying to get the fruit temperature under control. So if you've got 5 days of excessively high temperatures in the storage, those fruit are ripening, and they're ripening 2 to 3 times faster than they normally would. This kind of information has been known for years. Here's some data from 1924, just a few years after commercial refrigeration began. You can see rapid ripening, slower ripening, and slower ripening yet at the lowest temperatures. And just to drive home the point, this is from 2019, some storage that went wrong in a room in Washington State. So I'll pick on you guys out west for a little bit. But we have room 10 here, which is under normal control. You can see the reduction in temperature as time goes on. So I got the fruit under control. But one particular room had a breakdown in the refrigeration, had the spike in temperature, and had another breakdown in refrigeration at the end of the year. And as a result, if you would look at cumulative respiration over time, and I'm using that to sort of give an indication of what happens to overall metabolism, meaning ripening. Yeah, that room was far different from all of the other rooms in that particular storage, and that room was a complete loss. And so it can happen. It can happen in Michigan, can happen this year, can happen next year. Everything needs to be managed accordingly, according to what the condition of the fruit is as it comes into storage. So I think about it this way, finishing up just with simple kinds of concepts. Fruit are designed to be consumed. They're not designed to be stored biologically, evolutionarily. They're supposed to be consumed so that we consume seeds and the seeds are dispersed. Storage environments are stressful. They're at low temperatures sometimes, too low for some varieties. They're too long for other varieties. So we have to store them at low temperature for long periods of time. That is stressful on the product. So when they've already been stressed in the field by high temperatures, it's exacerbated when you put them in low temperatures and then hold that storage duration out for some extended period of time. Apples are variable, cultivar to cultivar, year to year, lot to lot. So this is the kind of thing that is really important to understand. If you think of them as nuts and bolts, as commodities, then you're not looking at an apple fruit the way it really is. So one lot is different from another lot. I think everyone understands that, but we really have to bring that in, inculcate it so that we think about it in terms of monitoring and managing. Marketing is unpredictable. So what you put in storage, you don't know when it's going to be sold. Humans make mistakes. And in the case of that storage where we weren't monitoring properly, that's a really good example of that. And then on top of all of that, we're seeing signs that the climate is changing. So all of these things are working together to make it a difficult job to store. So if I were to just make some summary comments, control maturity to the extent that you're possible. And I use the word control because we actually do have pretty good control means out there, whether it's retain that we're using or pre-harvest 1-MCP applications. Control ripening with post-harvest MCP. We can do that also with temperature, AVG to some extent. We need to monitor. We need to monitor prior to harvest, at the time of harvest, and then after the fruit have gone into storage, pulling samples out, making sure that the quality isn't declining beyond marketability. And then manage marketability. So those people that are monitoring need to communicate with folks who are marketing and say, hey, we got to move a room. We got to move a room. Yeah, you can't just sit on the fruit. You'll pay for it. That's all I have to say. This is just something from Ohio today. High temperature breakdown, I assume, but yeah, it's an ongoing problem.